Yeah, I hope my Wi-Fi is fast. Running on 5G. So okay, I'm recording. So once again, welcome to the second lecture for MA4002 Fluid Dynamics. I believe this is where we last stopped. Correct me if I'm wrong. Okay, so I think the last time we managed to derive the Bernoulli's equation, and from first principles, at the end of the day, we managed to basically derive the Bernoulli's equation. Now, even though the Bernoulli's equation seems to encompass quite a fair bit of flow scenarios, we always have to be mindful of its limitations. All right, we just cannot apply it anywhere for all scenarios, because there are some limitations due to the assumptions that we make when we derive the Bernoulli's equation. Okay, for example, all right, Bernoulli's equation should only be applied towards invisible flows or flows whereby viscosity is zero. Okay, it should be applied to steady flows only. Okay, and at this present time, we should only apply Bernoulli's equation when the flow is incompressible. And last but not least, okay, the Bernoulli's equation should be applicable along the same streamline only. But of course, right, we do take liberties with this in terms of its application. Sometimes we don't quite really apply just along streamline. Okay, but we apply Bernoulli's equation along the same flow path, if you will. Okay. So now, if you think about it, if you look at this equation over here, since we have basically, I think previously we have mentioned that Bernoulli's equation is actually a statement of energy conservation. Okay, whereby the total energy at this point along the streamline must be equal to the total energy along the same streamline. Okay, that means that the summation of the energy terms of the various energy terms must be the same, the summation, not the individual terms, because the contributions can vary, of course, depending on what's happening with the flow. But the total energy of the various components must remain the same. Okay, so now take a look at this equation below. All right, so basically this statement will stand. Okay, if we assume that Bernoulli's equation is applicable along the same streamline or flow path, meaning let's say we have got two locations, point 1 and point 2, as indicated by the subscripts here. That means I can write the summation of P1 divided by rho g plus V1 squared divided by 2g plus Z1. All right, it must be equals to the summation of P2 divided by rho g V2 squared divided by 2g. And Z2 at another point. All right. Please note that there's no flow losses incorporated here. There's no increase in the flow energy, right, by a device within the flow path. Okay. I'm not too sure whether I've gone through this before, but now I'm going through again. Now this first note here that has got a static pressure here. Okay. This the static pressure term as the numerator. This whole term here is known as the static pressure here, or just pressure here. Okay, the second term here that involves the velocity, the square of the velocity. This is known as the velocity head, or kinetic head, or kinematic head, depending on which text example you speak to. Okay, now this term here that involves the height term, or the z term. This is known as the elevation or gravitational potential here. Okay, now some of you guys might be curious why we use head and head. Oh, it's just a very, very old term to describe energy. Okay, so I think we're still using it as a matter of tradition, I suppose. Okay, all right. So don't worry about this. What the hell is this here? Okay. Okay. Now let's go back to Navier-Stokes equation, which I think we covered the derivations. All right, and came up with the full set of expressions. Okay. Hang on for a minute. Let me just go on. I think I. Okay. Okay. Now let's go back to simplification of Navier-Stokes equations. Now, I think we have earlier seen how we can simplify Navier-Stokes equations, because the full Navier-Stokes equations can be too hard to handle because it's just too many terms. And we've seen that if we are able to assume viscosity equals 0, we're going to get the Euler equation and so on and so forth. Okay. Now, assuming mu equals to 0 or viscosity equals to 0, to simplify the Navier-Stokes equation, it's not the only way that we can simplify the Navier-Stokes equation. Right? For example, we can assume that, oh, we're dealing with 2D flows. So if that's the case, that means I can set W, velocity component, to 0, and all the del by del Z terms to 0, right? For if we assume that the flow is just 2D. Okay, we can even assume that the flow is 1D, and you can make further assumptions. And by setting, let's say, V equals to 0, del by del Y comes to 0. So as you can see, right, more and more terms of the Navier-Stokes equations can be so-called neglected or cancelled off. We can also assume that the flow is stable. Right? If that's the case, that means any fluctuating term with respect to time t terms, all these can be set to 0 as well. We can also assume, right, the flows are fully developed. Okay, a fully developed flow means that the velocity changes, the velocity profile, okay, do not vary in space. Okay, so for example, that means I can set, let's say, del u by del x equals 0. If, let's say, the velocity u does not vary as we propagate, or as we move to different x locations. Okay, that's another simplification that we can make. Or instead of assuming viscosity equals to 0, which is not very ideal because we know that viscosity can't be 0, what we can do is we can set viscosity to be a constant. All right, okay, and some of the terms can well, that means let's say some of the terms, let's say, maybe one of the term is del mu by del x, we can set it to 0 as well, and so on and so forth. These are by no means an exhaustive list of the kind of simplifications we can make, but some of the common ones. Okay. Now, so because of the fact that we can't really simplify way too much, that's the trouble. Okay. And also, all right, it's hard to basically account for all sorts of flow scenarios. Okay, we can only so-called simplify and solve Navier-Stokes equations for very, very simple flow, because the trouble with fluid dynamics is that the flow phenomena are all very, very nonlinear. And it's only under the simplest of flow scenarios that we can make assumptions confident. Okay, so for example, all right, still we are able to solve Navier-Stokes equations, put in reasonably sound assumptions for, let's say, scenarios such as flow above a flat plate, for boundary layer flow, flow between flat plates, or co-act flow, whereby we have one moving plate and one stationary plate. Okay, and the procedures associated with simplification of Navier-Stokes equation, all right, is basically first thing first, all right, make all the assumptions that you need to make. Okay, don't be overly aggressive, of course. Okay, so basically, once you simplify, terms can be neglected or set to 0. And after that, think about it. All right, Navier-Stokes equation is at the end of the day, all right, most of the time described in partial differential terms. And after simplification, we're supposed to integrate, all right, and apply boundary conditions to solve the unknowns that arises from the integration process. And basically, all right, we will be able to arrive at a solution if we're careful. Okay. But of course, right? I mean, it seems like, that's fantastic, isn't it? We can simplify Navier-Stokes to our heart's content, all right, and then we get a very nice equation. But the thing is, all right, you've got to be very careful. Of course, right? Mathematically speaking, you can simplify whatever you can. But the trouble is, all right, your simplified Navier-Stokes equations, all right, you have to ask yourself this question: do they still resemble the actual flow? You've got to be careful. Mathematical simplification is one thing. Resemblance to the practical flow phenomenon, that's another thing. So one of the biggest problems with simplifying of a Navier-Stokes equation, especially if you choose to ignore viscosity, basically say that I'm happy with all the equation, right, is that anything that has got to do with viscosity, right, will not be taken into account. For example, skin friction drag. Okay, because skin friction drag, right, is usually will have to be estimated from the Newton's viscosity law. And Newton's viscosity law basically tells us that the washer stress and hence the skin friction drag, all right, it's a function of the product of the fluid flow viscosity and the velocity gradient at the wall. If we set mu equals to 0, there's no skin friction drag at all. Okay, and things like flow separation behavior will not be able to be predicted, because why? You need to have the boundary layer for flow separation to happen. But boundary layer can only happen if you have non-zero viscosity. All right, so you've got to be very, very careful. Okay, so what happened is sometimes the simplifications are so restrictive. Okay, and we are only able to come up with analytical solutions for really, really simple flow scenarios. Sometimes they are not that useful. Okay, but it's a good starting point, nevertheless. Okay, so what we tend to do in Navier-Stokes equation is to make as few simplifications as possible, actually, and basically, right, basically we make use of the whatever equations that we have with, right, and basically solve them by CFD, all right, by simulations. Okay, basically we crunch the numbers. Now we have to come up with codes that basically describes the partial differential equations. Okay, and basically, we set time t equals 0. These are the initial conditions, right? And then progress to the next time step. Let's say time t equals 0.001 second. All right, and then basically get the velocity field, the pressure field, and then progress t equals 0.002 seconds, and so on and so forth. So as you can see, it's a very, very tedious process. So some flow simulations, all right, can take up to a couple of weeks to a couple of months on a supercomputer. Right? Okay, now back to how we may simplify Navier-Stokes equations. I'm going to just go through a few classical examples so that you guys will know how it's being done. The first example, we're looking at flow between flat plates. So as you can see from the figure here, the shaded region here, this will be the top plate, this will be the bottom plate, and we have a fluid that's flowing between these two parallel plates. Okay, let's not complicate matters. All right. Okay, we can always say that look, it's a divergent plate, right, or it's a convergent plate. But just for the sake of simplicity, let's stick to two parallel plates. Okay, so now if you think about it, right, if the two plates are stationary, so surely something must be driving the fluid. If not, the fluid should remain stationary. Right? There need to be energy input. And in this case, the energy input surely must come from some sort of a pressure gradient that's produced by maybe a fan that's blowing the fluid, that's blowing air between these two parallel plates, or maybe there's a pump that's moving water or other fluids through this flat plate. Okay, so pressure gradient, all right, should not be zero in this case, because other than that, nothing will explain why the fluid is moving. Okay, and as part of the simplification, okay, perhaps, okay, we can treat this as like a purely a 2D flow or 1D flow actually, all right? So, but first thing first, let's assume that the plate length, okay, are infinite. So these are two gigantic parallel plates, so there are no end effects, okay? Let's assume that the plate width is infinite as well, that means into the paper, okay? That means the velocity, all right, behavior should not matter. Doesn't matter what's the z direction. So that means we can set w equals to 0. Okay, no the velocity component into the paper. Okay, and in this case, all right, let's not complicate matters. Okay, let's assume that the flow is incompressible, but yet with a non-zero viscosity. Right, that would be more realistic, isn't it? Okay, and again, just to simplify matters even more, reasonable simplifications. Okay, what we can do is let's assume the flow is steady. Okay, if the flow is steady, any del by del t terms will go to 0, right? Okay, and that u, that means the velocity u, right, the horizontal velocity component u, varies with, right, the distance between the location between these two flat plates, that means very wide only, based on the coordinate system here. Okay, such that u is purely a function of y only. That means we can express u as a function of y. Okay, now let's continue. Let's consider to begin to so-called get some simplified expressions. Okay, right. And also to just to prove to you guys that u is actually a function of y. You can start off by considering the mass continuity equation del u by del x plus del v by del y, which is 0, isn't it? This is the mass continuity equation. Okay. So now if you take a look at this flow field, you realize that all the velocity components, okay, there's actually only one, and that is only in the horizontal direction. So if that's the case, okay, v is always 0 then. If that's the case, if v is 0, del v by del y must be equal to 0. If del v by del y equals to 0, substitute back into this, that means del u by del x equals to 0. If you do a partial integration, you realize that u surely must be only a function of y only. So this is how we prove this statement over here, this assumption. Okay. Now moving on. Okay, since we've got the three different equations of the Navier-Stokes equation, let's start off with the one that's associated for the y direction, with the y direction. And this is how it looks like. Okay, we have del v by del t plus u del v by del x plus and so on and so forth. Okay, for the interest of time, I'm going to do it without the whole expression. You guys can see it. Yeah? So now, based on our assumptions, okay, if you think about it, since we're already assuming that the flow is steady, that means there's zero acceleration. So del v by del t can be assumed to be zero. So this term goes to zero. And since v equals to zero, that means plenty of these terms can be set to zero as well. In fact, all these terms can be set to zero. Okay, and if we assume that gravitational effects are negligible, okay, that means we can set Fy here to be zero as well. Okay, if that's the case, after cancelling all the terms that you're able to cancel, all right, after reasonable assumptions, okay, what you will get is at the end of the day, all right, you're going to be left with this del p by del y is zero. Now, if you do a partial integration, you realize that p surely must be a function of x only. Again, this is just to prove to you guys, right? That things can be as simple as it gets, so long we make the right assumptions. There's a question from Sung Hin. Basically, the question is, I think he or she, all right, saying that for this scenario, it is a non-zero pressure gradient in the x direction. That's correct. Okay, it's going to be a non-zero pressure gradient because if you think about it, if the plates are moving, why is the fluid moving then? So surely there must be a source that produces the necessary pressure gradient to drive the fluid forward. Okay, all right. If the fluid is moving on its own, I don't know. It sounds stupid things are going on. No, we're scientific. Okay, we're engineers, we don't believe in that. Okay, so some device must be providing the energy, all right, that leads to the necessary pressure gradient that drives the fluid flow forward. Yeah. Okay. Yeah. Okay. All right, people. I know sometimes I just crack. I just crack jokes here and there. Of course, that's me. All right, that's partially nature, but I think it's actually more important that when it comes out to lecture doing all this online stuff. Right? And let's take it easy a little bit. I'll be a bit more chirpy because life is depressing. I think I'll try my best. I think I should try my best to make things a little bit more fun for you guys if you guys don't mind. Okay. All right. If you guys do mind, okay, then I will not crack any more jokes anymore. Okay. I'll just keep my big pen face. Okay. But I hope not. Eh? Okay. Okay. All right. Now we have considered the y direction equation for the Navier-Stokes equation. Let's consider the x direction. In fact, this will be more important because think about it, the flow is actually moving in the x direction. So this particular expression, all right, that's associated with flow in the x direction, will be quite critical. So as you guys can see, this will be the expression that's associated with the x direction expression of the Navier-Stokes equation. I know that's quite a mouthful. I know that's quite a mouthful. Try to follow it. Yeah. Okay. Again. All right, based on the similar flow condition that we considered early on, can make the appropriate assumptions, and I'm not going to go through in too much details. You guys can figure out for yourself. All right, most of the systems can be set to zero, such that at the end of the day, we're going to get this expression. All right, del p by del x, that's the pressure gradient in the x direction. All right, and it's actually equals to mu, that's your viscosity, dynamic viscosity, mu into del square u by del y square. Remember what I said about simplification of Navier-Stokes equations? Once we have these partial expressions, what do we do next? Okay, what do we do next? We do an integration. Okay, remember it's a partial integration, not a full integration. Yeah. Okay, I'm quite sure you guys know how to do it. So we can integrate this 2 times because we have del square u, right, by del y square. We should integrate this partially 2 times, right, such that we are going to get an expression for the velocity u, and u, all right, can be expressed as 1/2 mu into dp by dx y squared plus ay plus b because we integrate 2 times. Right? Okay. Now, in this case, please note that it's we're no longer writing del p by del x in a partial differential because earlier on we've already established that the pressure gradient is only in the x direction. Okay, so we can just write it as dp by dx directly. Okay, so now we have got 2 unknowns of integration a and b. Okay, surely we have to solve for these unknowns, right? And we can solve for these unknowns by imposing boundary conditions. Like, for example, we know that at y equals to 0, u must be equals to 0 because you're at the wall, right? No slip condition. Okay, and by imposing this boundary condition, we can find out that b is actually equal to 0. So rinse and repeat. Let's apply another boundary conditions because you've got two unknowns. Then you have to come up with two boundary conditions to solve the two unknowns. Okay. So the second boundary condition we're going to apply is that when y equals to d, that means at the other plate, that means the top plate. Okay. At y equals to d, u is actually equal to 0 as well. Okay. And we can work out that a is this constant integration. Well, it's nothing but minus 1 over 2 mu into dp by dx d. Okay, so substitute this into this, and since we know b equals to 0, you can get the full, I'm sorry about that. Then we can get the full expression for the velocity u. So u equals to 1 over 2 mu dp by dx y squared minus dy. Now we know, from the equation, because there's a y squared term, that the velocity profile must have a parabolic shape because there's a y squared term there. Okay, right? Because of this y squared. Right? That's why the velocity profile is not a flat velocity profile. It's not like some string shape, but because there's a y squared term, it varies. So u is a function of y squared. So there's a parabolic velocity profile. Now there's plenty of stuff that we can do once we have gotten this expression. For example, we can make use of this expression to deduce the maximum velocity in the flow. But surely it must be at the center, right, because of the parabolic nature. Okay, but what's the expression? This is what we're interested in. So we can make use of this expression to get the maximum velocity and where the maximum velocity actually happens. Now, how do you find maximum and minimum points? Okay, just do a partial integration, a partial differentiation and set it equal to 0. If you do that, you set it to 0, okay, the location of maximum velocity is y equals to d over 2, which is not surprising, as we said, right? It's supposed to happen at the center line if the velocity profile is a parabola. That makes sense, okay? Then we can substitute y equals to d over 2 into here to find out u max then. And u max can be described by this expression. Okay? All right, and that's all to it. All right, but of course, some of you guys may wonder, hang on. U max, okay, but why is there a negative term? Are you telling me that the velocity actually the flow reverses? No. There is a negative term here. Nothing is wrong here. There is a negative term here because you know what? Because dp by dx is actually a negative term, right, for a flow that's moving from left to right. Okay, with the frame of reference that we used earlier on. Okay, because dp by dx, by definition, is P2 minus P1, the downstream pressure minus the upstream pressure, all right, divided by the downstream distance, the downstream location minus the upstream location, x2 minus x1. So P2 must always be less than P1, isn't it? Okay, because the pressure gets lower and lower if you go further and further downstream. So that's the reason why, right? Okay, why we have a negative term for U max, because dp by dx is always a negative term. Okay, now how about wall shear stress? If you think about it, we have got the velocity term. All right, surely if we're able to find the velocity gradient, we can estimate wall shear stress. Yes, we can. Now, the ability to calculate wall shear stress will come in handy if we were to estimate the wall skin friction strength. Okay. Now, how do you calculate wall shear stress? Wall shear stress equation is defined as such. Now, this is the Newton's viscosity law. You guys might want to write it down. So we have wall shear stress, tau W. W stands for wall. Okay. All right. It's nothing but the product of dynamic viscosity mu and the velocity gradient del U by del Y at the wall. Okay. So now early on, we know that del U by del Y. All right. I've got this expression. Now, so what happens is at the wall, right? Surely y must be equal to 0. If y equals to 0, we substitute 0, or y equals 0 to here, we're going to get a simplified expression for del U by del Y at the wall, minus d over 2 mu into dp by dx. Take this, plug it into here, and you can get the expression for the wall shear stress, tau W. So as you can see, right? Once we have got an analytical solution for u, for the u velocity component based on this flow, okay, we're able to derive a lot of other terms as well. Okay. Now let's move on to the next example, which is one that deals with co-ed flow. Okay, a co-ed flow, as I mentioned earlier on, basically is a flow between two flat plates. However, one plate remains stationary while the other plate is actually moving at a fixed velocity. Okay, so the scenario can be represented over here. So the bottom plate here is the stationary plate. The top plate is actually moving from left to right. Now, ask yourself, if the top plate is moving from left to right and the flow is between these two flat plates are moving, do you really need to have a pressure gradient to drive the fluid forward? Actually, no, right? I mean, we could have, but it's not necessary, unlike the previous case. Okay, so in this case, right, fluid will move from left to right simply because the top plate is moving from left to right. The top plate is just dragging it, right? Okay, intuitively, all right, even though it'll be shown later, we know that the velocity variation should be a linear one. Okay, but it will be shown later as we work towards an analytical solution. Okay, so now let's assume the top plate is moving from left to right at a constant velocity, u, that's it. Okay, and the gap between these two flat plates once again is d, and then we have this coordinate system. Okay, so a lot of the flow conditions are quite similar, right, to those that we encountered in example one, but of course there's some subtle differences. Okay, but in terms of simplifying the Navier-Stokes equation, I think we don't have to go through again, but suffice to say that we're going to get this again. All right, we're going to once again, after simplifying Navier-Stokes equation, we're going to get del P by del X equals to mu into del square U by del Y squared. Okay. However, remember what I said? The fluid is moving from left to right simply because the top plate is moving from left to right, not because there's a fact. We could add a pressure gradient term. Okay, just to make things more interesting. But in this case, there's no need. So let's assume there's no pressure gradient produced by a fan or compressor or anything. So we can set del P by del X equals to 0. And if that's the case, that means del square U by del Y square, all right, is actually equal to 0. And we're supposed to integrate this, okay, to get the velocity distribution, isn't it, between the two flat plates. So you do a double integration, and you're going to get U equals to AY plus B. Okay, once again, we have two unknowns, so we impose two boundary conditions to solve for the two unknowns. Once again, at Y equals to 0, U equals 0, because of no state condition. B can be worked out to be 0. Okay, the other boundary condition surely must be one that is associated with the other plate, right? So, and the other plate is actually at Y equals to B. But we know that the velocity of the plate is UE. Okay, and that also means that the fluid velocity U right at the wall then of the upper plate, or the top plate, must be equals to UE because it knows the condition. And A can be worked out to be UE divided by D. Okay, substitute this back into here. All right, you're going to get a rather simple expression for the velocity variation. So U is nothing equals to U into Y divided by D. Now take note, Y over D is actually a linear function. So basically, this statement tells us that the fluid velocity between the two flat plates is actually a linear function of the velocity of the top plate. All right, and hence it's linear. Okay, that's why it's linear. Oops, that's why it's linear. All right, there's no Y squared term here. All right, okay, so it's not parabolic. So once we have this, once again, we can come up with expressions for the wall shear stress, just like what we did previously. Okay, and in this case, the wall shear stress will have this expression. All right, you guys can sort out the details. I work out the details or some steps are simple. Okay, and that basically concludes chapter 1 of part 2 of MA4002. Okay, we have altogether 4 chapters, and I think we are making good progress. Yeah. Okay, because this week is week 8. All right, so we have hang on, week 9, week 10, week 11. Week 12, week 13. So I've got 5 more lectures, okay, to clear 3 more chapters. So I think we're making good time. Okay, so I don't want to rush through all these chapters because once I rush, I find that students just get confused. Okay, all right. I'm going to just close this slide and share this thing and share the next chapter. So far, so good, people. If you guys have got questions, now's the best time to ask. Miscellaneous, I mean general questions. Not like how do you differentiate, so how do you integrate this device probably more specific conversation. Just pull up. On the next chapter, we're going to be looking at will be potential flow theory. Okay. Oops, why is it full screen? Slideshow, set up slideshow, browse by picture window. Okay. Okay, I hope you guys can see the slides. Give me a thumbs up if you can. Because sometimes when you switch slides to one floor. Yeah. Thank you very much. Yeah. Because earlier on, before this lecture, I had an online lab. And I think the lab manager was trying to play my recorded video on his PC and share on this MS Teams things. And strange enough, we only hear the video, but we don't see the video. Sorry, we hear the audio, but we don't see the video. All right, and then we fumble a little bit here and there. Yeah, so of course, MS Teams and Zoom, all these are quite reliable most of the time, but once in a while you get hiccups in there. Right? Okay. All right, so yeah. Okay, so welcome to chapter 2, people. Okay, so for chapter 2, we're going to talk about potential flow theory. Okay, and I must say, potential flow theory is a highly mathematical theory. It is a very old theory. Okay, back when people, all right, had got no idea there's such a thing called fluid viscosity, and hence this theory assumes zero viscosity. Now we know that, all right, and I think I've mentioned earlier, once you assume zero viscosity or assume that the fluid is invisible, right, it means that a lot of the flow phenomena are not going to be accounted for. And that's the reason why there are some outstanding issues with simple potential flow theory that we're going to cover. In the sense that some of them may not resemble a real life. But think about it, right? This theory is quite old, 100 plus, 200. Okay, so back then, this was what they had. This was the best that they had. Okay, now some of you guys may start to have this question coming up, say, oh, why are we studying something that is so old? Why are modules that ends with mix, like thermodynamics, fluid dynamics, mechanics? Why are we studying very old theories? Okay. I'm quite sure you guys have heard, right? All these are some oldies are still goodies, not all, not all oldies, but some oldies are still goodies. Right? So I would say that potential flow theory is actually one of them. Okay, it allows us to be able to get estimates of simple flow scenarios based on a mathematical construct, rather than to perform experiments or to do simulations. Sometimes, right? Okay. If the scenario that we're dealing with can be described more or less by potential flow theory, we realize that the formulas are there for us to apply and get some estimates relatively quickly. So the key thing when it comes out to potential flow theory is we have to make sure that we have to judge, okay, whether the flow scenario can use potential flow theory. Okay. So there are limited scenarios that you can use it, but there are other scenarios whereby you can use potential flow theory. Okay, this is a scope. I know it's quite a list, but maybe I'm just being too meticulous, right? Okay. All right, but don't worry, right? The scope of this particular chapter will cover some background, right, with respect to the potential flow theory, when we can use it, when we should not use it. Okay, what do you mean by irrotational flow and rotational flow? It's not so simple. When it comes out to rotational flow, we're not simply talking about flows that seems to rotate. There are other considerations to be made. Now I'm going to introduce you guys, ladies, by some new terms such as vorticity and circulation. Right? What do we mean by streamlines and stream function that describes the streamline distributions? What do we mean by velocity potential lines and the function that actually describes the velocity potential? How we can express, how we can, how we can learn potential flow theory, okay, based on different coordinate systems, which are the two coordinate systems that we could use in this module. And after all this background information, the introduction to the potential flow theory, okay, all right, it's only then we'll move on to, all right, the more so-called useful, more realistic potential flow scenarios. Okay, we're going to cover basic 2D potential flow entities such as free vortex and false vortex. What's the difference? We're going to be looking at superposition of basic 2D potential flows because of the fact that potential flows are based on the linear mathematics. So we can literally add them. Okay. And once we add them, we're going to get like very interesting scenarios. There are infinite ways of combining. But some of the more useful ones will be a doublet scenario, whereby you superimpose a source and a sink. Right? You can also combine a source with a uniform flow. And we'll see what we're going to get at the end of the day. And to make things even more interesting, you can say that, look, I'm not happy with just a source in the uniform flow. I'm going to add in a sink in a certain way. And what do we get at the end of the day? We're going to be looking at doubling uniform flow, and we'll realize that it's going to resemble flow, a particular flow scenario, whereby a 2D cylinder is immersed in a uniform flow. And how we're going to get because of the equations that we derive for doubling uniform flow to solve for flow past a 2D cylinder. Because some of you people might have done this wind tunnel lab experiment in year 1. Okay, some of you guys. Remember you have this desktop wind tunnel that flow past a circular rod? Yeah, so there's a 2D cylinder. 2D cylinder basically means a very long circular cylinder. And last but not least, we'll look at rotating cylinder flow. That's probably the most interesting flow scenario. Okay. Okay, some background information with respect to potential flow. Okay, now potential flows, right? Okay, theory. Potential flow theory is basically a set of theory that's devoted to the study of fluid behavior under very, very idealized flow conditions. Okay, for example, right, viscosity is always 0. We talk about potential flow theory. The flow is always steady. And at least for this module, the flow is always 3D. Okay, there are 3D potential flows. Okay, but I think that's just too much. Okay, 2D potential flow theory is already tough enough. So it's best for everyone. Okay, so again, I think I mentioned this. Right? Okay, sometimes you have to ask yourself. Okay, fine, we can always assume mathematically that viscosity is 0, but does it even make sense? Always ask yourself this, does it make sense? I think it's very, very important. Don't just blindly say that, look, this is I have to learn, I just use this, I get the answer, I get all about it by next week. I don't think that's good. I don't think that's good. I think we should be able to understand the rationale. Okay. So since all real fluids has got non-zero viscosity, even for air, as low as it is, it's still non-zero. So why are we still looking at potential flow theory? Okay, the reason is that certain scenarios, okay, depending on what kind of scenario, okay, I'm going to give an example. Certain scenarios has got very little viscous effects. It means has got very little effects, has got very little flow behavior that's directly affected by the non-zero viscosity. Okay, all right. For example, right, let's say flow past an aerofoil. Okay, maybe I'll just move on to the next slide. Okay, let's say flow past an aerofoil or flow past. So what happened is, typically speaking, okay, for such flow scenarios, okay, we know that there's boundary layer over any solid boundary. Okay, whenever there's a flow. But for a particular scenario like this, flow past an aerofoil, okay, the aerofoil tends to have a rather thin boundary layer in relation to its thickness, to its cut length. All right. So yes, even if you look up close, the boundary layer is so thick. All right. But then again, I'm urging you, okay, take like, I don't know, 200 steps back. Okay, can you still see the boundary layer? All right, this figure. So the boundary layer will be this tiny little layer here along the upper surface and along the lower surface. So you take like 200 steps back. Can you actually see the boundary layer? No. Right? So what I'm trying to say is, okay, scenarios such as this, or any scenario whereby the boundary layers are very, very thin, okay, we can assume that any the viscous effects that give rise to the boundary layer can be neglected. And we're interested in the pressure field, the velocity field, all right, just outside of this boundary layer. All right, and if that's the case, then potential flow theory will be applicable, or at least give us some decent estimates of the pressure field, the velocity field, and so on. Okay. All right, there are other flow scenarios other than this. Okay. Now, as promised, okay, we have to differentiate what I mean by irrotational flows and rotational flows. Okay, I'm just going to put it out there. Okay, when we talk about rotational flows or irrotational flows, we do not really particularly mean whether that flow, that control volume or control area of the particular flow area, is it really spinning? When we talk about rotational or irrotational when it comes to fluid dynamics, we're talking about whether they are being deformed about a particular point. Okay, all right. Unlike something that's solid. Okay, unlike something that's solid. Okay, there's no way to deform them. So if it spins, it spins. Okay, although I apologize, this my kids are magnetic. Okay, anyway, so see, if it's a solid, if I talk about solid mechanics, whether it's rotating or not, I think it's quite clear. All right, if this thing rotates, everything rotates at the same time. All right, this point rotates at the same angular velocity at this point. Okay, however, you have something that's all the props I've got to use. So imagine this is like a controlled volume of fluid. I'm quite sure you guys will realize that, depending on the forces experienced by this control volume, it may be deformed. Oh no, this is quite okay. It may be deformed. All right, and it may be deformed while it's rotating. So see, for fluid dynamics, right, the idea of rotational flow or irrotational flow, whether it's undergoing deformation or not, while it's spinning at the same time, becomes a lot more complicated, and hence that explains all the various equations that we have to deal with. Okay. Just give me 1 minute. 1 second. Someone text me. Okay. Oh, you guys are chatting about. Oh no. Is it windy at where I'm at? Hearing this choppy sound. Oh, are you guys still hearing that? Please let me know. Sorry, I didn't check. Okay, hang on, because I'm giving this lecture at the dining table, so I should show the front because I close all the windows and stuff. Hang on. Is it better now? Can someone let me know if it's better now? Okay. It's not too loud, right? I hope. It wasn't so loud just now until you guys can't hear me, right? It's just some background noise, right? I hope. Please let me know it's not so bad, or else I have to record everything again. Okay. But you guys could hear me just now, right? It's just that there's some annoying sound. That's all right, I hope. Okay. All right. Now that things are better. Okay. Thank you very much. All right. Thanks very much, Nicholas, Brandon, Yingxian, and Kang Yu. Okay. Thanks very much. And yeah, Fiona. Okay. Okay. So let's get back to the lecture. Thanks for letting me know. Yes, you guys have to let me know, right? Okay. I appreciate that. Okay. Anything that we can do to make this lecture better, right? Clearer. I think that's always good. Okay. Back to this slide. Okay, so as I've mentioned earlier on, okay, when it comes out to fluid motion, we have to be worried about fluid deformation as well, and whether the fluid is deforming, right, or not actually allows us to judge whether the flow is irrotational or rotational. Okay, now to explain this better, okay, let's take a look at this control area. Or control volume. Let's assume, let's assume it's unit length in the paper. Right? So it's essentially 2D. Or you might want to assume that it's infinite length in the paper. That's fine as well, right? So we're going to have an X and Y coordinate system, and let's say the fluid area or the control volume or 2D control area can be represented by this rectangular here. Okay, and let's say we label the points O, this vertex as O, this vertex as A, and this vertex as B. And let's say this rectangular control area has got dimensions of delta x, let's say, along OA and delta y along OB. And since we are talking about fluid motion, let us further assume that along this edge, the fluid velocity is u. And along this edge, the fluid velocity is v. Okay, now, how about the fluid velocities along this edge and this edge then? If you think about it, right, since this is fluid motion, surely there must be fluid velocity gradient. All right, if the velocities are not zero, surely there must be velocity gradient. So let's assume in general terms that the velocity along this line, or this edge, okay, is nothing but the velocity v here, plus del v by del x, that means the velocity gradient between this edge and this edge, multiplied by delta x, which is the distance that separates between separating these two edges. All right, following the same line of reasoning. Okay, that means the velocity along this edge, okay, can be written as u plus del u by del y, the velocity gradient between these two edges, multiplied by the distance between these two edges, which is delta y, and that's why we have got this expression. Okay, so now all the four edges of this 2D control area are now defined in general terms. Okay, all right. Now let's assume that something happens to the fluid, okay, such that OA, this HOA, begins to rotate anti-clockwise, and OB begins to rotate clockwise through a tiny angle. In this case, OA will rotate through a small angle, delta alpha, and OB will rotate through a tiny angle, delta beta. Okay, so and let's assume that all this happens within this particular time interval, delta t. So that means, since we are assuming small angles, that means the displacement from A to A prime as part of the rotation, okay, can be described by del v by del x times delta t. Okay, and the extent of movement from point B to point B prime can then be approximated as del u by del y times delta t. Okay, so now with all these things set up, okay, hang on, there's still, I see some chats in the video. Oh, okay, no, from another chat. Do you know I'm having a lab right now as well? Having a 3-hour lab, the lab manager is helping me. All right, so they're asking questions there. All right, while I'm having this lecture, it's this online thing. Okay, anyway, we'll do our best. Okay, now with all this, so basically, all right, we have got this deformable square thing, and then we're just sort of like doing this. Okay, now since it's rotating, all right, it's been deformed and been rotated about vertex O. We'll be interested in finding out at what angle of velocity are they rotating. All right, because this rotation is going to deform the 2D control volume. Okay, so now, oops, sorry about that. I think I better use keyboard. Okay, so the angular velocity of OA, okay, it can be approximated as omega OA, all right, equals to, all right, the limits of what? Del alpha by del t as del t approaches equals to 0. It's for very, very tiny angular changes. Okay. All right. And if we go back to this and inspect this particular area here, we realize that if we take tangent of delta alpha, that means the small angle through which OA is being rotated, delta alpha, tangent of delta alpha, and because it's small angle, can be approximately equals to delta alpha. All right, and delta alpha, if you think about it, if I take tangent of this angle, it's nothing but opposite divided by adjacent. Opposite, we've seen that it's actually del v by del x times delta t, and adjacent is actually delta x. Then hang on, we got some terms that we can cancel off. And we can state that at the end of the day, delta alpha is approximately equals to del v by del x times delta t. Now, we take this term, since this equals to delta alpha, plug it into the earlier term that we have got for this omega OA, the angular velocity of the edge OA. All right, and the angular velocity of OA is nothing but del v by del x. It's nothing but just the velocity gradient, as an approximation, of course. All right. So now, if we're able to derive that for the angular velocity of OA, right, which is rotating, That means you can do the same thing for OB, right? Because it's rotating the other way around. Okay, and we can find out that omega OB is nothing but del U, or should I say that can be approximated as del U by del Y, yet another velocity gradient. And by definition, the net angular velocity, all right, associated with the deformation, right, can be defined as this. The net angular velocity, omega, note that there's no OA or OB, this is net angular velocity, can then be defined as omega into half of del V by del X minus del U by del Y. Now, again, some of you guys might say, hang on, why is it minus? Okay, all right, it's minus because you know why? In fluid dynamics conventions, all right, the directions matters. And in this case, for anti-clockwise rotation, all right, it's positive. Counterclockwise rotation is negative. All right. So if you have a minus sign there, all right, basically you are just adding, all right, the angular velocities, right? Okay, if you think about it, all right, and then we divide by 2. So this is by definition. Okay, but I think the most important thing here is to appreciate the fact that the angular velocity associated with the deformation is actually a function of velocity gradients only. So velocity gradients, or the fact that we have different velocities at different points in the flow, actually, all right, causes fluid deformations. I think that's the biggest takeaway. Okay. Now, which brings us to this term known as vorticity. Okay, vorticity, all right, has got a symbol. It's represented by a symbol called zeta. It's written as this way. Okay, you guys should start to practice how to write. Okay, zeta, all right. Now, vorticity, what is vorticity? Vorticity can be seen, I think for your level at this point, I think it's sufficient to see vorticity, right, as the swirl or rotation of the flow. Okay, remember, it's not just if the vortex is rotating. We should look at it as the rotation, all right? When we see a fluid rotate, we should say that we should ask ourselves, is the fluid being deformed rather than just simply spinning around? Okay, so vorticity can be seen, all right, as the swirl or the rotation of the flow. All right, mathematically speaking, it is known as the curve of velocity, and it's actually defined and related to the angular velocity. In fact, it's defined as zeta equals to 2 omega. But early on, we already found out the definition for omega. So bring the 2 from the denominator here to the left-hand side, and all we'll be left with will be the velocity gradient differences. So zeta is nothing but del V by del X minus del U by del Y. And the best thing about zeta is this. If zeta equals to 0, right, okay, for that particular control area, control volume, that means the flow is known as an irrotational flow or potential flow or ideal flow. They all mean the same thing. Now, if zeta is not equal to 0, that means the flow is actually rotational or is a non-ideal flow. So meaning, right, if it's an irrotational flow, that means the fluid does not suffer, right, a net deformation. If it's a rotational flow, that means the fluid suffers, all right, non-zero net deformation. Okay, now you realize that this is in 2D terms, right? Okay, there's no Z term or W term. It is always possible to have a vorticity term, right, that's defined in the 3D control volume as such. Okay, now before I end off this slide and let you guys go for a break, all right, it is important to note that just because the flow is an irrotational flow, okay, it doesn't mean that the flow is not rotating. Okay, and rotational flow doesn't mean that the flow is rotating too. Remember, it's whether the flow, all right, is deforming as well. So a good example would be later on we encounter the idealized free vortex, all right, vorticity equals to 0, but it's actually spinning. But vorticity equals 0, right? Because there's no net deformation. All right, and boundary layers in real life, okay. All right, even though the boundary layer can be a laminar boundary layer, whereby the flow is moving straight and through, right, in the laminar layer, right? But vorticity, I mean, there's no rotation, but vorticity is not equal to 0. Okay, so you got to be careful when it comes down to what I mean by irrotational flow and rotational flow. Okay, all right. Okay, I think I'll just pause here. We still have about an hour to go. Yeah, so I think I'm going to pause here. It's been quite a long lecture. So please go for a break, about 10 minutes break, and then we'll come back again. Okay, I will stop the recording, go and stretch your legs, wash your faces, and freshen up. I will, I will stop my recording then. I'll see you guys back in about 10 minutes. Okay, all right, thank you very much. Please don't log off, huh? I'll see you guys back in a minute.